So, ladies and gentlemen, my name is Petr Kluson, and I'm here together with Professor Martin Pu, representing European Federation of Chemical Engineering, and we organize the previous week and this week we have organized and we are organizing the Spotlight Talks, the autumn series, which is already it was organized this year already for spring, and before during the COVID period. It's a series of lectures on various topics delivered by working parties of the European Federation. We are very happy that you decided to actively participate, and I'm very glad that Fabrizio, Bezzo, professor from the University of Padova, decided with his colleagues to organize a special spotlight talk devoted to sustainability and security of energy and associated critical supplies in challenging times. I like challenging times. I think that we have critical times rather than challenging times, but there are plenty of topics to be addressed, and we have 3 lectures today. Before passing the stage to Fabrizio, I'd like to ask Martin for one slide to be shared, which is here to tell you about the nearest activity of the European Federation. It's within or below the umbrella of the European Forum on New Technologies, which we organize annually. And in December, 5th of December, in Paris, we are going to meet because of establishing or founding a completely new section of the European Federation of Chemical Engineering, which is called Chemical Engineering as Applied to Medicine. I do believe, or all of us strongly believe, that it is a hot topic. We still have some free places for registration. So if you are interested in this, and I think that this is a really pushing issue topic for chemical engineers. So don't hesitate and register for the one-day event in Paris on Monday, 5th of December, in 2 weeks. Okay, so that's all from me. And now I would like to invite Fabrizio for his introductory introduction to our afternoon session on very interesting topics. Thank you.
Thank you, Peter, and welcome to everyone for this afternoon talk organized by the Section for Energy of the European Federation of Chemical Engineering. The Section for Energy, I was the former chair of this section, is dealing in fact with all energy-related issues concerning chemical engineering, which is in fact quite a lot. So from, say, new and renewable fuels to energy integration, to energy storage, biofuels, and so on. As Peter said, this afternoon, in fact, we will focus on something more specific, which is about sustainability and security in energy, especially in these complicated times. And we have 3 speakers. Dr. Colin Axon from the Brunel University in the UK, Dr. Mariano from University of Salamanca in Spain, and Dr. Aidong from University of Oxford, again UK. Then I will say a few words more about our speakers. Anyway, I think we can start immediately. Just a few organization details. If you have any questions, please type them in the Q&A section that you can find in the Zoom panel, and I will pick them up either at the end of each talk or at the end of the session. So I think we can immediately start. So the first speaker, as I said, is Colin Axon. Colin is a senior lecturer at the Institute of Energy Futures at Brunel University, London. He has a long experience and publication record on energy risk sustainability in chemical, mechanical, electrical, and transport engineering. He held positions in Bath and Oxford universities, and today he's going to talk about the causes of risk in fuel supply chain, and also how this might change the way we think about future energy scenarios. So, Colin, the floor is yours, and we will just hear what you will be saying us.
All right, thank you very much. Here we go with the screen share. Oops. Hopefully that is visible.
Yeah, it is.
Thank you. So what I'm going to describe this afternoon is some work that Richard and I have been working on for quite a number of years, and we're going to simply summarize some of the key findings. I'll give some links to some papers at the end where you can find all of the detail should you be interested to find out more. But we have been thinking about all sorts of problems in sustainability. I'm also very much interested in energy, and what we noticed was that measuring energy security was not as intellectually mature as measuring or assessing sustainability. And we thought there should be some way of taking some of the methods and techniques from measuring sustainability and applying them to energy security. And what we thought about, or what we realized, was that although energy security and sustainability have many features and characteristics in common, there was a key difference, and that is how risk is handled within the framework of sustainability or the framework of energy security. Sustainability is intrinsically backwards looking. Energy security is very much forward looking, although both do go either way. But the thing about energy security, which sustainability doesn't necessarily pick up or doesn't automatically pick up, is the fact that there are risks, occurrences, accidents, some things, practices that have not yet occurred, and therefore there is no data about them. And in case of some very serious risks, accidents, what have you, we hope they never do occur, or they have only occurred very rarely. And sustainability frameworks don't handle that terribly well. So we concentrated on thinking about how risk affects the two ways of thinking. Now, you will often see security of supply being synonymous with energy security, and I contend that they are not the same. They have different meanings and different purposes. So electrical engineers and electrical power engineers are very content with the idea of security of supply, and that's the second by second keeping the lights on operational matters, which extends into days and weeks and months, because no strategic decisions could be implemented that quickly. So everything at that point is operational. You just have to make the best of what you've got, whatever that system is. But going sort of to the length scales of a year, 5 years, 10 years, that is very much the realm of energy security, because decisions can start to be implemented, changes can be made. But in the case of, say, deciding to build new nuclear power plants, say, you're looking at decadal length decisions and build processes. that starts to get into the realm of sustainability, which is intergenerational. And in the end, as fossil fuels are finite, the energy system must become completely sustainable. So there is a blend. Now, these are not hard and fast boundaries, but out of it, we think about, and everything that you'll see from now on, from me today, long-term energy security we see as being approximately or very similar to think about it as sustainability. That's just the context. So as chemical engineers, we've thought about how do we split up the process. We want to think about risk, and I'll come to that, but I mean, what are we dealing with? Well, we don't want a system that is so complicated with so many pieces that it's impossible to, it's just not tractable to analyze, but there needs to be some granularity. So and of course, we're looking across all fuels, of which we identified 25, 19 of which are relevant to the UK, but whatever our analysis is, it's got to be able to cope with all these fuels that are old and tried and tested, fuels that are currently being used, and fuels that have been thought might be possible in the future. And so the analysis framework has to accommodate all of those quite disparate things. So we've gone all the way from exploring for resources, which is essentially measuring how much of something there might be and assessing that, to actually exploiting, that's the second stage, actually extracting that resource in whatever way, conditioning that raw material, converting it to a final energy vector, distributing that final energy vector in an appropriate way to an end user, which would is not just residential, but residential, commercial, industrial. Okay, so everything from individual household all the way to large sites. When thinking about, and this will have an implication for levels of risk, some of these fuels, you'll notice, say with solar and wind, exploiting the raw resource, the raw fuel, in that case is the motion of air, wind, or photons, sunlight. That is we have to treat those as a fuel source. The exploitation, conditioning of that fuel and the conversion to the final energy vector, in the case of solar and wind, an electron, that is all done in one single object, and that has an implication for risk. Anyway, these all in the papers you can see. So we got 25 fuels in total, each of which have 6 stages, and we identified 34 causes of risk in 7 categories that reflect the whole of the fuel supply chain. That's a big analysis exercise. I'll show you the risk in detail a bit later. We do a standard risk matrix approach using data and knowledge from various sources to assess the likelihood and impact of each of the risks. The numbers in here don't matter. These are just some examples. What I'd like you to observe, though, is that the seemingly, quote, good renewable sources are not free from high-level risks, although there are lots of low-level risks, and the fossil fuels and nuclear are not solely high-level risks. They have plenty of low-level risks as well. And this sort of peels back and reveals us a set of information which perhaps can be used by policymakers, investors, to perhaps target interventions more wisely, or to get more bang for the investment buck or the research buck, and rather than having sort of blanket interventions which will work only in parts and be wasted in others, say. So the point is that the fossils have more high-level risks than the renewables, but it is a mixed picture, and we think that is important to understand. So if you do all of the analysis and bring it all together, it won't come as any surprise. I've normalized the risk scores here, and they're not weighted for resource availability, and I'll come back to that. It's not altogether surprising that unconventional gas, shale gas, is at the top. In fact, gas and oil, that is predictable. Nuclear fission, that's perhaps predictable that it's near the top. However, in terms of risk, it is near the top for different reasons from oil and gas. What might be surprising, and I emphasize this is for the UK, geothermal energy is also very high risk, carries a lot of risk, huge amount of investment essentially, and you drill lots of wells, and you spend an awful lot of money, and you may not get a return on that. The thermal store may simply not be big enough. So there are lots of risks. So that's perhaps surprisingly high. What is surprisingly high, but entirely justifiable, are the bioenergy routes. So whether that's solid gas or liquid. And that is, I mean, it's a surprise to a lot of bioenergy researchers, but the fuel sources that are being used, anything from agricultural waste to forestry waste to energy crops perhaps, the variability of the fuel source is really wide. And that makes processing more difficult, more expensive. There might be extra stages. And a lot of that processing is very similar to what the oil and gas industry might use. It has the same sort of levels of complexity of oil refining and gas cleanup and so on. And so if you're going to do that at scale, it's not surprising that the bio routes carry quite a bit of risk. It's not surprising that the renewables are down the bottom, but solar thermal water heating, very dependent on whether you've got south-facing roof, the amount of resource that you can actually extract from that is not that great. So you can't just say, well, we'll as a national energy strategy, we'll just start at the bottom and work our way up. You can't do that because of the fact that not all of them are able to deliver in quite the same way. Hydro is very geological dependent, geology and geography dependent. Ground source heat pumps, that's thermal low temperature. If you haven't got the space, it's not a possibility of use for you. Demand reduction is sitting there somewhere in the middle block. And so you might say, well, surely energy efficiency is known as the first fuel. Surely that would be down the bottom. Demand reduction is not just energy efficiency or energy conservation. It goes beyond that. It is about reducing the overall envelope of energy use. So that is persuading people and companies and organizations to change behavior, change patterns of use to reduce the overall demand, not just have a more efficient device that you had than you had previously. And trying to persuade people to change behavior is extraordinarily difficult and very it's underestimated. And if you treat it as a risk that somebody won't change their behavior, that is why that is much higher, or is in mid-table rather than being at the bottom. And that, to all my energy demand reduction friends and colleagues, is a big surprise. But if you think about the risk, it's not so surprising. What you notice though, and this is observable in the real world, is that it's simply easier to add some more supply in terms of PV and wind, especially, than it is to try and persuade people to use less in the first place. So that's interesting, or at least we think that's interesting. These are the causes of risk. We've used a sustainability process analysis method type approach to derive these. And then they say these were evaluated at each stage for each fuel. They have scores. These are in rank order. So most risky at the top, least risky at the bottom. Remember, this is for the UK. What you'll observe from this is that we contend that our method of analysis is fair and unbiased and reasonable, because you can see that the different categories of risk are spread throughout, from top to bottom. They're well spread, and all of these 7 categories are represented in the top 10 most significant risks. So we think we've got a robust method here. We tried this out with a workshop with some industry experts, only one academic, and there were people who represented consumer groups as well as generators, investors, and so on. And we asked them not to do any ranking. They didn't see this list at all to start with. We just gave them what are the list of risks, and they, without knowing our ranking, they came out very clearly and said, changing regulatory and policy framework is the most significant risk for them in their industry. And this was across the board, whether it was renewable or non-renewable, whether they were consumer groups, representing consumer groups, or industry users. This came out as the top risk. And as you can see, we had found that it was the second most important risk. So we're in good agreement there. And you can see that they recognized the other set of risks, not in rank order, that they came out and said, these are important, not quite as important as the policy framework, but very important. And as you can see, they were clustered towards the top. It's a relatively small sample, so you read into that what you will, but we thought that was a good validation of what we had come up with. So that's interesting. So what can you do with it? So you can take, you'll be familiar with future energy scenarios of various flavors, and every nation has them. And what you can do is, I've done this for, on the left, for the installed or the projected installed electricity generating capacity, because each of the fuels has a risk score, as you've seen. We can, by proportion, work out how much risk is associated with each of the elements of the portfolio that's projected into the future for each of these scenarios. And therefore, we can then calculate what the risk profile for that scenario is. So this is just installed generating capacity. CCC is the body which, the Climate Change Committee, which advises the UK government, and that's their net zero pathway. The national grid, that's the UK national grid, the grid operator, transmission system operator, has their own scenarios. That's NG, and they've got a reference, and their LTW is essentially a net zero pathway. And there's another set of scenarios from a model called 7C, which is a biophysical energy whole economy model, which I rather like. I'm biased about that, but it's a solid piece of work. And there's a reference scenario and fastest offshore wind and fastest new nuclear build. The risk profiles for all those scenarios, you can see, is they're quite different, although some of them converge, although in terms of the installed capacity, don't necessarily so. Taking just a quick look at the CCC and the orange triangles and the green triangles, you can see they have very different trajectories in terms of installed capacity, but look on the right-hand side with the orange and green blobs, their risk profiles very similar. So that we think is an interesting extra tool for helping make decisions. Thinking about the greenhouse gas emissions from those scenarios, I've just used National Grid and CCC here. Again, the greenhouse gas emissions profiles out to 2050 are declining, but significantly different for different reasons. Because National Grid think that they're going to have to pick up the slack for decarbonising transports and heating, transports, whereas the CCC assume that liquid fuels will be decarbonised. That's why there's a big difference there. But their risk profiles remain similar. I think that's very interesting, and simply looking at the greenhouse gas profiles, you would not be able to predict that. It's another tool for how do you go about making decisions. This particular work is in review at the moment. Hopefully that will come out. So in summary, we have a method which can be applied to the nation state or a set of nations perhaps. It is transparent. You can see that from the papers. We lay it all out. It is repeatable, it's self-consistent, and we put in some checks and balances to minimize the assessment error rate, which I've not told you about, but it's quite neat. It will be that list of fuels, that rank order, and the rank order of the causes of risk will be different for different countries. The UK is perhaps not that dissimilar from other European nations, but it's you can see that the nations in, say, the Southeast Asia might have a very different set of profiles from North America, from Europe. So it's widely applicable, and we think it's robust. And if anyone would like to collaborate with us in different nations, we're all ears. We found that the spread of risk, not only between the fuels at any one stage, but throughout all stages, varied. So the risks are not for a particular fuel are not the same at every stage. And that's, we think, something that's important. We were able to also identify some systemic risks from this as well, which is useful. And we've applied it to a future energy scenario, future energy system portfolios. And so we think that this is a useful tool for governments and policymakers and electricity network operators, say, to think about how they target policy and interventions or investment indeed. And there I will stop, say thank you very much, and happily take any, if there are any immediate questions about clarifying anything I've said, we'll do that. Otherwise, please have a think and we'll answer questions at the end.
Thank you very much, Colin. At the moment, we don't have questions, but I repeat to the participants, if you have questions, please use the Q&A tag. However, I have a curiosity, Colin. You talked about risk, and then you said that risk is somewhat, at least in terms of time, something between present day issues and long-term sustainability. But I mean, according to your experience, what is in a way the correlation between risk and sustainability? When risk becomes sustainability, and can you see any clash between risk and sustainability goals in a way?
It's actually a key question. You've actually got straight to the heart of this. I don't actually have a good answer for that at the moment because we haven't really bottomed that out. We've recognized that really in so many ways, the security and sustainability, and actually it doesn't matter whether it's energy security, it's security, the concept, and sustainability are in so many ways interchangeable. Yet there's this one key difference, and exactly how to incorporate future risk into a sustainability framework we haven't properly bottomed out yet. That is actually work in progress. But we are making some progress, and we've just got nothing really at the moment to say about that. So I can't really answer that question other than ask me back in a couple of years.
Okay, sorry, we lost you again in a couple of years for a new spotlight talk about the correlation. Thanks a lot, Colin, for the very interesting talk. And now we can move to the second speaker, who is Dr. Mariano Martin from University of Salamanca. Mariano is associate professor of chemical engineering there. He also leads the sustainable processes and products lab. He worked at Procter & Gamble and was also a Fulbright scholar at Carnegie Mellon in the US. He has a long list of publications, over 160, dealing with several topics concerning energy, but not only, and especially in the process systems engineering area. Also, he published several chapters in books, and so on. And today he will talk about a multi-scale approach that can be employed for resource exploitation towards energy security. So, Mariano, I'm eager to listen to your talk. Please, the floor is yours.
Thank you, Fabrizio, for the introduction. I'd like to thank also the European Federation for giving me the opportunity to share the work that we are generated here from the University of Salamanca. As Fabrizio introduced, the topic we are going to be discussing is how chemical engineering, in particular process engineering, can help in this transition, or at least to produce or generate an energy system that is somehow more stable than and not such affected by the situation, to mention something. So basically, over the last month, we realized that Europe is in a weaker position compared to what we thought it was. Basically, the problem has been our reliance on resources that were not ours, that actually, even though the oil, gas are available up to a certain amount, actually we are buying it from certain places. So what we have in our place, what we can actually use is renewable resources, but the problem with them is basically, as most of the people in this audience know, is the availability. So basically there are two different resources that we can use, either programmable ones such as residues, biomass, waste, or non-programmables, solar and wind. Here, for instance, today in Salamanca is rainy. The solar availability, even though typically is high, today we cannot rely on that much. However, wind is higher. So basically the problem is how to handle, how to manage this availability so that we can actually maintain our quality of life. Basically here in Europe, at least in the south of Europe, there is the solar irradiance is quite large. Italy, Greece, Spain, Portugal, and to the north, we find that the wind velocity is actually quite large as well. So as a result, the idea will be how we can actually use those resources and deal with the challenge of their availability. Together with that, we can also see how the different residues, forest residues, harvest residues, are distributed across Europe. As a result, we can actually make use of them in order to produce fuels, in order to be able to somehow mitigate the variability of the others. So what we present here is the possibility and the need for a more integrated way to process those resources. And instead of just focusing on the one hand, the process and separately the supply chain of the products, we have to be able to accommodate and to develop a more integrated system that considers altogether the generation, the transformation of the resources, and the supply chain, together with operation and control, because in the end, the variability, what makes is the need for such integration of resources over time. So what we present here actually is what the title of the presentation somehow discusses, is a multi-scale approach all the way from the evaluation of the availability and characterization of the residues, the resources across different regions, across the different classes of them. Once we have that, and basically we will be using geographical information systems in order to provide some structure of the data and to be used for further analysis. We need to evaluate the process. The process, when we deal with these different, for instance, different waste, the different biomasses, the problem typically is that the different residue behaves differently. The pretreatments change, the operating conditions of such pretreatments, as well as the yield. So basically, we have to adjust and we have to evaluate each one of the different residues, each one of the different biomasses, or in the case of wind and solar, we have to consider how the facility will operate under the different conditions across the region of study. For years, chemical engineering actually has used the concept of economies of scale, basically because larger facilities will not proportionally increase in cost. However, in the case of distributed allocation, distributed availability of resources, apart from scale up, we have to also consider scale down. So basically to evaluate the proper size of the facility depending on the availability and the region of study. And finally, we are going to consider the formulation of what is called as a facility location problem, basically in order to be able to select the type of facility, the type of residue, the type of resource, and where to allocate them. One important feature is the fact that we no longer consider only economical indexes or economical objectives, but also environmental and social. In many regions across Europe, and in particular here in my country, in Spain, there is the population basically because people look for jobs in different regions, and as a result, there is what is called empty regions. So the development or the installation or the deployment of a new energy system can help mitigate such social problems. So just paying a little bit of attention, because we've already talked about this multi-scale, but multi-scale means not only process and allocation, but also the fact, as I mentioned before, related to the different resources, the fact that we have to be able to analyze the different resources because they affect the yield. So we have to go all the way from the unit analysis, experimental data, first principles models, in order to evaluate the yield from the different resources, put together a process that will allow us to evaluate the economics and the yield, so that this is the process that is going to be evaluated and installed at some point. One of the particular features of these processes is that sometimes the processes can be divided into different stages, in the sense that, for instance, when we talk about biomass, the moment we generate syngas can be used for a number of different products. So a facility can select the processing of biomass to produce syngas, and later, depending on the allocation, depending on the needs, we can obtain different products and install different facilities as a result. The third stage, basically, after analyzing the availability and evaluating the process, is the scale up. Typically, we are somehow familiar with certain rules for a quick scale up of the process, but we have to take into account the different units and the different scale up rules for the different units. So this process of scale up or down affects not only at the size, but sometimes also the technology. That means that, for instance, when we are separating air, larger processing capacities will consider, for instance, distillation, while if we go down, we go to smaller production capacities, we change into different technologies, and that also affects the cost and creates certain discontinuities in the analysis. We have to consider, on the one hand, the OPEX, the operating conditions, but operating cost, sorry, but also the CAPEX of the facility. Typically, because of the analysis of these processes, mass energy flows will allow us to scale up the different units, unit by unit, and it will be possible and easy to scale up the process as as a combination of all of them. It is also important to consider water consumption, which is somehow has been forgotten for years. Moving on to the last stage, and I mentioned already before the consideration of social indexes. Apart from the economics of the system, we develop certain indexes in order to be able to account for the fact that the investment or the installation of new facilities may have on the generation of wealth. Then the generation of wealth in the form of jobs, and also in attracting people, and so at the same time reduce this movement and the population of certain areas. Basically, we are going to be developing surrogate models in order to incorporate the facilities features, their cost, the production capacity, the emissions, the water consumption, etc., as well as social issues, for instance, the jobs generated or the wealth generated. And maybe, in most of the cases, there is a budget limitation that will allow us only to install a number of facilities. So basically, with this method just presented, we are going to go over a number of examples related to the use of residues and solar and wind across different scales, all the way from my region to the country and all the way to Europe. So basically, if we pay attention to the management of residues such as manure, municipal solid waste, crop residues, and sludge, it is possible to create a circular economy that will allow us, on the one hand, to substitute part of the chemicals that currently come from crude oil, but also a little bit of energy, a lot of energy, we will see the results now, and reduce the need for mineral fertilizers. Because of its use in the community, we will still generate some residues that can be recycled to the as raw material, and also we will be able to continue our activity. Basically, this process is going to be using a digester. We are going to the fact that most of these residues contain a lot of water reduces the possibility of using some other technologies. Drying manure or sludge is typically really energy intensive. So the process is based on collecting these residues, which results in the need for either supply chain or the selection of the allocation of the facilities close to the ones that generate the waste, the generation of biogas, and the processing of the digestate so that we can recover the fertilizer. Basically, these facilities generate just a little bit of biogas compared to the amount of digestate and the fertilizers. So what it means is that the economics of these facilities is also heavily influenced by the possibility of selling or putting in the market this digestate. So one of the things that we have to also consider is where it's not going to be possible to put our fertilizer in the market. So in this case, we include certain constraints related to the availability of previous regions or previous facilities that already produce or already generate this digestate. So this is my region. This let me just, for your reference, I'm coming from Salamanca, so I'm speaking more or less from here. And if we consider the residues related to or to municipal solid waste, manure from cows and pigs, sludge from wastewater treatment plants, and lignocellulosic residues, and we use the budget available from the region to install infrastructure, which is 350 million euros a year, we see where and which kind of residue is going to be used to produce biogas. So basically, we are focusing on municipal solid waste, basically because there's already an infrastructure that collects the municipal solid waste in large areas, and also lignocellulosic, also because of the density. But one important result from this analysis is that, on the one hand, it is possible to produce 3 times natural gas consumed in our region just by using the residues. And in order to get to that, we need an investment that is typically between 10 to 12 times the budget available for 1 year. So it is feasible, but there is a barrier to implement this because that is the cost. Just with the 1 year budget, we can get, as you see there, the processing of 70% of the municipal solid waste, and actually total waste is 9%. So we can produce natural gas, and now that is we see the actual problem that we are facing, the use of residues can be a problem. However, this is only a region, so we have to move forward to a larger scale. And as I mentioned before, there is a problem in dealing or in managing different residues, the lignocellulosic, solar, and wind. Here is for the case of Spain. We will move on to the entire Europe a little later. We see the availability of wind in different regions, the availability of biomass and residues, and the availability of solar. So we come up with this superstructure of alternatives so that we can use solar and produce electricity via PV panels, concentrated solar panels, concentrated solar power plants. Actually, there are 2 different ways to cool them down, just wet cooling and air cooling. We have wind turbines, we have residues, we have biodiesel from residues, we have hydro, and we have also biomass. And there's a way we can store this energy by producing hydrogen and later capturing CO2. We can produce methanol and methane can be used in gas turbines, and also the methanol can be used directly for the production of biodiesel. One particular feature is that some of these facilities, for instance, biodiesel facilities, require energy, require thermal energy, and for them to operate, they need to produce the thermal energy in situ. So this network is going to be allocated in particular regions across the country. And in the regions where the processes require some energy, they need to be produced internally. They can be produced from, for instance, the use of part of that biomass. If we apply this to the entire country, to Spain, we go and we are able to, for instance, get to 100% power production, but with a reasonable use of area. Is not possible to go over 20% of fuels, diesel and gasoline production. This means 2 things, and we relate this result to some of the comments my colleague just made a few minutes ago. Actually, saving energy is one of the important ways. It is true that it's difficult to convince, but we have to also be careful because actually we are using more fuel, more gasoline, diesel than the one that we can actually produce easily. We can also see the reliance on hydro. So hydro energy is recommended in most of the places, even though we have to be aware of the fact that in some cases it's already available, and in some others maybe the geographical area will not allow us to build such a facility. So a more detailed study can be used for this, and also the fact that again the investment typically is quite high. So again, this is on a monthly basis, but we also did some studies related to how to integrate solar wind from a scheduling point of view, so that we will be able to organize and organize the use of the different resources in order to make it work. Another problem related to the current situation is that at least over the last years, coal or thermal power plants have been shut down in Spain. Nuclear facilities are reaching their final years of age. They are getting old somehow, and we have to substitute a certain amount. There's a problem related to the use of solar and wind. On the one hand, we need to be able to integrate them so that we can operate our system and meet the demand. But there is another possibility that the chemical engineering brings to the table. That is the fact that we can use the chemicals in order to somehow store that energy. There are different chemicals available, and here in this on this slide you can see the production of magnesium hydride. Actually, the idea will be to be able to produce hydrogen from renewables, but that hydrogen is stored for a short period of time to somehow absorb the variability, and we will be using the magnesium hydride in order to absorb the long-term variability, and later this magnesium is just decomposed with water, and that will release hydrogen, and that hydrogen will be used in a fuel cell in order to produce the power. So there are two things. On the one hand, we need to regenerate the magnesium oxide, to regenerate the magnesium from the magnesium oxide that is generated after the release of oxygen. So that requires quite a lot of energy, but the efficiency of such integrated facility is close to the one that typical power plants show with the Rankine cycles, around 30%. So basically, in that sense, is fine. And the second thing is the cost. If we take a look at the cost of the energy, actually, with the current prices of electricity, these facilities start to be promising. So in this sense, we have to realize that it can be feasible, but again, who is going to invest in these facilities that are the size of nuclear plants? So that's the main issue behind. Over the next year, it is expected that with the improvement in the efficiency of electrolyzers, fuel cells, PV panels, wind turbines, it is possible to reduce the electricity cost produced by these facilities and make it more competitive as well. These facilities can be used to substitute those who, for many years, have been providing the base load for the electrical system. And the idea will be to use or to consider different social issues, job generation, in order to help develop the regions by using the GDP as somehow metric to evaluate where to install the different facilities, or even to use this new energy system to fight underpopulation. And you see that depending on the different objective functions, the energy system changes. And this is actually some of the tools that we can provide for the decision makers to evaluate how this new system can help in this process. Basically, just to give some numbers, it is possible to generate up to 500,000 jobs because of substituting 16 gigawatts of power. But again, the barrier is the investment, because these facilities are expensive, but they are not much more expensive than the nuclear or the coal-based power plants that were installed at some point. Instead of this magnesium, the hydrogen economy is also moving into, for instance, the production of different fuels, different non-carbon fuels, such as ammonia. Ammonia can be produced from solar and wind, basically producing hydrogen and separating the air using power, basically is what you need for those. And you see that depending on the size of the facility, we have different technologies for the separation of air, from distillation for typically larger production capacities to membranes in case of lower. You see the production cost of the nitrogen and also in the end of ammonia as a result of the production capacity of those. Once you have the ammonia, we can develop a power plant based on ammonia. Nowadays, it is important to have a mixture hydrogen ammonia for that to be possible to be used in a gas turbine. That's the reason why that ammonia is to be partially decomposed to generate the hydrogen required for that combustion. And among the different alternatives, whether we have to treat or not the gases, whether we recover the hydrogen that is has not reacted or not, and whether we recovering the argon that is going to be used to control the temperature in the turbine. Actually, we have 8 different alternatives, and the one with the cycle yield that is around 40%, which is again competitive with the current power plants, is the one that doesn't require to treat the gases. We recover the hydrogen and we recover the argon instead of producing more argon from air. Again, the production capacity plays a role, at least in terms of production cost, but the production cost of electricity, we will see a little bit on the effect of the ammonia on that, but it is still high. But over the last summer, we've seen cost of electricity that were even larger than the ones you see on this slide. Again, this is related, or this relies on the cost of ammonia, and we see this sensitivity analysis with the effect of the cost of ammonia on the production cost of electricity. We see again the effect of the power capacity. For larger production capacities, it is possible to, as long as we get ammonia prices below 0.4 euros per kilo, the electricity costs are competitive with the values you see nowadays in the market. So these facilities can also help. And finally, this is a work in a collaboration with Professor Cravagna Group at the University of Maribor, and we extended the work into full Europe. And the idea will be to evaluate the transition all the way to 2050 from the status in 2020 and see what can we do. So considering again economic, environmental, and social issues. The problem, even though this is not intended to be a seminar for specialized people, the problem is actually really large. We are talking about millions of variables and millions of equations, but it is possible to help provide ideas on how to get to that 2050 100% renewable power and 50% gasoline and diesel. Actually, the limitation again is how much fuels we can get from them. So basically, you see how solar and wind are installed over time. We make use of the availability of the resources across countries and across the different regions. In terms of the production of gasoline, the availability of biomass in Central Europe is key for the production of that, as well as in the north, and production of diesel basically from residues, as you see in highly densely populated areas, is where that biodiesel is produced. And one final comment, the fact that it is possible to evaluate the problem from a country level, which means we are going to focus that each country more or less helps itself, or on a more integrated area, and that's the reason for the European to come to agreement. We see that if we deal with the problem from a united point of view, we realize that the cost, the economics, the environmental, and the social objectives are better in case of considering a larger, basically because we make better use of the resources across regions and across the territory. If you go to a country level, you are more restricted to the availability in the different regions, and as a result, the costs are higher and the sustainability is a little lower. So with this, I'd like to just conclude by commenting that energy security in Europe is key for our future, and we can go sustainable. It is going to be difficult first because of the barriers related to the investment, but the tools that we are generating and we are creating from the process system engineering field, as well as from chemical engineering in general, can help in that transition. It is possible to somehow replace the power production as of the demand of today, but it's difficult to get to larger substitution of fuels, basically because of the large consumption so far. Energy storage is an opportunity. We as chemical engineers actually can help because there's chemicals, catalysis, and so on that will help develop those such facilities. But in the end, the advantage of our work is that we can evaluate the alternatives and come up with solutions. I'd like to thank all the members of my group, PhD students, my postdocs, and master students because the work I presented is based on their thesis, their master thesis, their PhD thesis, and they are the ones running the case of study. Thank you very much for your attention. And if you have any questions, I'll be happy to take them.
Thank you very much, Mariano. Thanks a lot for the interesting presentation. I think you demonstrated how such modeling approaches may provide the tools for strategic decisions. I have a curiosity that in a way is a broad view question. According to your experience, what is the kind of acceptance, we may say, of such models at policymaker levels? I mean, are we able to provide indeed policymakers with solutions that comes from such sophisticated models, or still, I mean, we are speaking different languages?
Actually, it's a very interesting question. Precisely, there's two things. Over the last years, because we can easily get to the fuel, get to the gas, get to the oil, just paying a price, there was no such, somehow there was not such a drive in order to be able to be sustainable, in order to be able to make the most of our resources. What I'm feeling lately, basically also because there are some coordination and groups that are being created at national and international levels, is that because of the current situation, and the name of this seminar actually is behind that, you realize that the politicians actually are realizing that we are in trouble, and because of that they are paying more attention to what or how we can get to there. And actually, I got an email from the vice president of research in my university today of the group that is being created and from the southwest part of Europe countries, just to come to the energy issues, how to address them. So I hope that through results and the meetings in those groups, it will be possible to transfer those ideas into the decision makers. I guess that so far, because of easy access to cheap energy, it was not such a problem. But lately, because society is concerned about the situation, they are realizing, politicians are realizing that we need to do more, and it is possible. I don't know how far we will get, but it is true that so far presenting these models, these results into the political levels has been really difficult. So in the best case, some research institute or national labs were interested in that because somehow they were receiving questions from the government, but those results didn't reach to the decision makers. Lately, as I mentioned before, because of the different discussions with the vice president of my university and the universities in my region, actually is starting to be more open to our work. So let's see. As my colleague was mentioning, maybe in a couple of years we can get back and see if they were accepting our suggestions.
Yeah, I do hope so. And it is good to hear that at least something is moving. Okay, thanks again, Mariano. And now we can move to the last speaker from University of Oxford. Aidong Yang is associate professor there at the Department of Engineering Science. Aidong is a chemical engineer, mathematical modeler, and he has been working, let's say, in the wide area of process systems engineering, specifically focusing, especially more recently, on the modeling, optimization, and also the sustainability analysis of food, energy, water nexus, and also on the technologies and designs for CO2 removal from atmosphere and the industrial decarbonization. Today, Aidong will talk about some studies they carried out on understanding, in fact, the food, energy, land coupling within the context of localized food production with indoor farming. So, Aidong, the floor is yours.
Hey, thank you very much. I hope you can see my slide.
Yes, we can.
Okay.
Thank you.
Okay, thanks again. Good afternoon to everybody. Yes, so my talk will have an element on renewable energy as well, which is something that was extensively covered by Mariano. But I think I'm going to move away slightly from the pure energy perspective to something about the link between food supply and energy supply. So Colin earlier in his talk, he was talking about a very important topic about energy security. And I hope, we all agree the security of a food supply is probably just as important. In particular, I'm going to look at the topic of indoor farming as an option to increase more localized food supply, which is with the intention of improving the food supply security. So, but I'm going to look at these particularly from the angle of the connections between food and energy. So to explain the thinking and the fundings we have got, I would like to start with this warning given by John Beddington back in 2009. John Beddington was, I think at the time, he was the chief scientific advisor of the UK government. So I think he was at a event, I think it was a conference. He mentioned this perfect storm around 2030, where the global demand for food, energy, and water will be very significant. At the same time, the supply might be significantly disrupted because of climate change, which is basically shown on this picture. I think this warning was more than a decade ago, but I think it's still valid today. The world population has just passed the line of 8 billion, I believe, just a couple of days ago. So the demand is still there. And in terms of supply, looking at the challenges from climate change, I guess, despite all the good work that has been done by academia, by people in industry, and the government, I guess we are still clearly facing the challenges from climate change. So I think all the challenges are still there. So and these challenges are not really independent from these three sectors, energy, food, and water, because they are very tightly coupled together, often captured by the concept of nexus. So, so the nexus concept basically, I think, speaks two aspects. One is the interdependency between the three sectors. So, for example, to produce water and food, certainly a lot of energy will have to be consumed, and also to produce energy and food, a lot of water will be consumed as well. I think for food production, for example, about 70% of the world fresh water consumption is for that purpose, and about 15% of water consumption is by the energy sector. So that is one aspect of nexus, which is on the interdependency between the three sectors. The other aspect is the, if you wish, some kind of competition between the three sectors over what ecosystem or the natural resources can provide. And this is particularly true in terms of land. So to produce food, of course, a lot of land will be needed, particularly for conventional farming. On the energy side, for example, I guess a conventional energy production systems might not require a lot of land, but when we move towards renewables, talking about wind and solar, so these renewable energy facilities will be much more land intensive. So there can be potential kind of conflicts between food supply and energy supply, something I'm going to come back to later on in the talk. So this is about the connections between the three sectors. Now, if we just focus on the food supply, I have got a few pictures basically taken from various newspapers. I'm sure very many of us would recognize some of the pictures, the very empty shelves in the shops because of the COVID. And in the UK, we have a particular challenge of Brexit, which has caused a lot of disruptions to the supply, particularly in certain interesting areas within the UK. But I guess these problems are not really specific to the UK. In many other regions, from time to time, the food supply chain does get interrupted by either extreme weather or by other geopolitical conflicts or by other kind of social, economic, or political events. Now, looking at the general picture of food supply chain, I think everybody would be rather familiar with this picture. It's quite a long process, starting from the primary production to transport, processing, distribution, and eventually getting to household for final consumption. So if anything goes wrong within this chain, this can cause serious disruptions to the supply. Now, to reduce the risks, then people have looked at the idea of more localized or more regionalized production or supply of food, as somehow shown in this picture. I don't know whether you can see any details, but it's really about reducing the distance between where the food is produced and where the food is consumed. Ideally, these things should be co-located within a certain range of geography. So that is the idea of the possibility to reduce supply risks, and by more localized or regionalized supply, they also hope to further improve the food quality because the food might be more fresh. There's less damage to the ingredients, to the nutrients in the food. So there could be a benefit from the quality perspective. But the problem is, if we want to produce food more locally or regionally, there can be limitations from the, say, for example, the climate conditions, the availability of land. From the climate point of view, so if we want to grow something in the open field, conventional farming, the temperature has to be right. Yeah, it can't be too extreme. So in very hot and very cold areas, if we still want to increase localized food production, we have to use some kind of so-called controlled environment agriculture or indoor farming. And here we have got these two options. One is this plant factory, multi-layer growth, and fully enclosed with the temperature, humidity, and other conditions closely monitored and controlled. And the light is normally just by artificial lighting as well. Another option is a greenhouse, which also offers a more controlled environment, but it has got a greater connection with the environment. For example, it can make use some of the natural lighting, and it can have some degree of natural ventilation. So that represents another option. So we want to understand, so across different regions, to what extent the controlled environment agriculture possibilities like plant factory or greenhouse, how this can contribute to the increased production of food as an option to the open field farming. Now, to look at this, we thought there are a few questions we need to answer. The first one is on the energy demand. So you can see the connection between food and energy. Particularly, this is particularly relevant to greenhouse and food factories. So we will see later on, this can be rather energy demanding. And we need to understand in different regions with different climates, how the energy demand would look like. And because that would be a great contributor to the economic feasibility. And then we have an issue around the land requirement, because when there are a number of commercial developments around controlled environment, agriculture or indoor farming, and from these developments, sometimes we hear the claim that indoor farming, among other possible benefits, would save land because the per area yield would be much greater than open field farming. I think this is true just in terms of the growth. But on the other hand, if we take into account the need for energy supply, and particularly if we want to supply the energy from renewable resources such as wind and solar, the energy supply side may require a lot of land. So to really answer the question of how the different options compare from the land perspective, we need to calculate both direct, which is for growth, and indirect, which is for energy. We need to combine direct and indirect land requirements so that we can have a more complete assessment. And finally, still around land, the land issue, after we have quantified the land requirements for each option, we need to look at different regions and to compare that with the local land availability, because one option which might be suitable for one region where land is plenty might not be suitable for another region where land supply is rather stressed. So that is another thing we said we wanted to look at. So how do we answer these questions? Well, again, we have done some modeling exercise. So we modeled the plant factory system and also the greenhouse systems. These things are not what chemical engineers often model, but actually, if you look into these systems, they are rather familiar to chemical engineering. So we have a large air handling system involving cooling, heating, and refrigeration. Within the growth space, we need to model, say, the plant growth, which is not quite common for chemical engineering, but we do have the temperature regulation, humidity regulation, and also the light supply, which are very much engineering. So I'm not showing the details of mathematical models, but we had to model each of these two different CA types. And beyond the modeling, we also need to optimize each of them because these are the two options. Now, in order to draw a fair comparison, we have to optimize each of them so that we compare them on their optimum forms so that the comparison can be fair. Again, there's a lot of details I think I'm not going to get into, but roughly speaking, the optimization problem is about looking at the hourly operation across a typical year. We need to determine how to do heating, cooling, lighting, and ventilation so that we can maintain the condition of either plant factory or the greenhouse within the right temperature range, which is shown by the red area here, and also the inlet and outlet humidity area, which is shown by these dashed lines. So I don't think we have time to look at all the details, but very quickly, in this picture, this is for a plant factory. So this area and this area represents the use of artificial lighting, and these bars here shows the intensity of ventilation. And this is for greenhouses, it's very similar. So the target of optimization is to operate the system within the required temperature and humidity ranges so that we can minimize the specific energy consumption, which is to produce 1 kilogram of vegetables, how much energy we have to consume. We want to minimize the energy consumption. So that is the first modeling task. The second modeling task is to look at land use analysis. So for open field, it's more straightforward. We just need to get the yield figure for different regions of our interest. For the CEA, we needed to look at, I think this is similar to what Mariano was talking about, looking at for each region and for each demand profile, we need to understand land requirement if we try to supply the energy from, say, solar PV or from wind turbines. And this is to quantify the absolute land requirement. And as I said earlier, then we need to embed these into the local land availability. So for that purpose, we needed to understand for each region of interest, how much land is available for renewable energy generation and how much land is available for agriculture. So these are the modeling tasks. And in terms of the scope of the work, just briefly, if you're wondering what kind of things we think we're going to grow, so we designed kind of the basket of vegetables. So this is mainly about vegetables, not for carbohydrates. And the target is to supply 50% of recommended nutrient intake for every region that we have modeled. And what regions? Well, we modeled across the world. We chose 9 urban regions. This covers different continents and different climate conditions, population densities, and also land availability. We have got a couple of regions in the rather cold areas and a few on the hot areas like Singapore and UAE, and a few in between. So this is the range. Now, just a little bit on the results. So on the energy requirements, so for the 9 regions, we have calculated the average plant factory energy consumption and greenhouse energy consumption on a per kilogram of vegetable species. And you can see that plant factories are certainly much more energy intensive. A greenhouse is better. For greenhouses in the very cold and very hot regions, the energy consumption is a bit high as expected. For the other regions, they are much more energy efficient compared to food factory. We also calculated for each area. So if we say we try to supply 50% of our RNI for that region, and how much of the currently produced energy in that region will have to be used just to support CEA, to support plant factory or greenhouses. You can see quite significant percentage. I think for greenhouses, it looks reasonable or acceptable for most of the regions, but for plant factories, the percentage can be very, very high. So that points to the feasibility of energy supply in the very much upscaled CEA sector. We talk about land use. So here we show the combined land use across different regions. So every region we have 3 bars, one for the open farming, and then we have the one for greenhouse and another one for the plant factory. So this is a combination of the land required for growth and land required for energy generation. The energy generation can come from wind and from solar. There are some details. I think I'm going to skip these details, but in terms of comparison, we can see a few things. So first of all, if we consider the combined land use, the indoor farming is not necessarily saving land. So in areas like Stockholm in Sweden, for example, and also in areas like Chile, it looks like the CEA would consume more land than the open field farming. In some areas, in a number of areas, the indoor farming can save land, particularly with the greenhouse option. But for some other areas and for many areas, particularly the plant factory option is not really favorable in terms of land use. And finally, just to show a little bit on the analysis of the land requirement against the local or regional land availability. So this picture looks quite complex, but let me go through this very quickly. Sorry. We have different colors showing different regions. The solid circle is for plant factory. The dashed circle is for greenhouse. And on this x-axis, we show how much land we can save for growth if we replace open farming with indoor farming relative to the total land available for open farming. So that is x-axis. On this direction, we show the renewable energy land abundance. That means the total land available for a renewable energy generation versus the renewable energy land required for just supporting CEA. So you can see some of the regions would enjoy a lot of land available for renewable energy generation, which is okay. But on the other hand, we want to look at to what extent we can save land for growth. Along this direction, you will see the most favorable locations. That means they have got a lot of renewable energy land available, and by implementing CEA, we can save quite some land from the agricultural operations. Well, unfortunately, not many countries are of this category. I think only this is UAE here, and this is Iceland here. For all the other countries, either you're not going to save a lot of land for growing, or you do not have enough land for renewable energy. And there are even regions where the full-scale CEA is simply infeasible from the renewable energy land perspective. For example, I think this is for Singapore, and this is for plant factory for Japan, for Tokyo in Japan. So that means even if you use, in this Tokyo case, even if you use all the renewable energy land only for CEA, you can only satisfy 40% of the demand. And it's even worse for Singapore. That means for these regions, from the renewable land availability perspective, it's not feasible to have a full-scale CEA. Okay, so quickly, let me wrap up my talk. So we're looking at the potential of CEA greenhouse versus a plant factory. You can see that greenhouse might be better than a plant factory, but there seems to be a kind of tension between the resilience perspective and the sustainability perspective, because for the use of CEA, we might be able to shorten supply chain, but on the other hand, for sustainability, we do need to find enough land to produce renewable energy, which is not always possible. And we were able to come to these kind of conclusions by combining engineering optimization and regional resource analysis, which seems to be quite important for answering questions of this kind. Finally, let me just thank the key contributors. I think that the main person who have done the work is Theo Wittner, one of my PhD students, supported by a few other colleagues. And finally, just acknowledge support from the financial, the funders. Thank you very much.
Thank you, Aidong. Thanks very much for the intriguing analysis. Can I ask you one thing? I mean, clearly your analysis was devoted to assess the possibility for localized farming. However, in a way, you demonstrated that there are some constraints in that, either because of land availability or what you call the resilience as well. Would it make sense in a way to, let's say, apply this technology, but keeping a global supply chain, in the sense that, okay, I will use this technology, but I will invest more where it is convenient, and then I will transport the food where the food is needed and maybe less convenient to use it. So a different optimization, we may say.
Yeah, I think that's a fair point. I guess the motivation of this work is to look at, if we run the food system very, rather independently, at the regional or local scale, what would happen? So certainly there are, regions where the indoor farming is more suitable than the other regions. But I guess, and then you could, as you mentioned, you could just run these facilities at the locations which are more suitable, and then you can distribute the products. I think that is certainly what many people are thinking of. I guess that is slightly different from the angle of this research, because in that case, you are still having this more globalized supply chain, which would still suffer from the same kind of risks as what we have today. But in terms of commercial operation, that is certainly something that could be done.
Okay, thank you. I don't see any questions, but let's say before we close, I mean, let me maybe just ask one question to everyone as a sort of a final discussion. Let's say what we saw today are tools, methods, models for making choices, we may say. So, for instance, Colin discussed about tools and metrics to analyze and assess security in energy. Mariano presented several examples of models that can be used to define, in a way, the best configuration. So again, the best choices we can make to set up an infrastructure. And Aidong did something similar in a way for a specific problem that was about localized farming, considering energy and so on, and to provide an analysis and again tools and metrics to decide what can be done and what is best. What about constraints, in a way, at a very in a broad understanding, in my opinion? So we provide, let's say, tools and metrics. We say this could be the right choices. What do you see as general constraints we may have for an actual implementation? So, for instance, I don't know, Colin, okay, you provided metrics, but when you go to policymakers, what do you think are the constraints they may have in using those metrics? And the same for Mariano. For instance, you talked about capital investment, but could be many other things. And the same with you, Aidong. Okay, you provided let's say, the right solution, but practically, what are the constraints for implementing the right solution, at least in your opinion? We can start from Colin, I mean, so we can keep the order of the talks.
Okay, thank you. The term "the right solution" for policymakers or those making decisions, that's an interesting term. I might take issue with the use of right or correct, because what is good for an individual, a household, a company, or a city may well not align well with what is good for the nation. Certainly politicians, not necessarily the professional policymakers as the civil service within the government, but the elected politicians. Whether we like them or not, whether we like what they do or not, they are trading off different constraints from what we do as various intellectual or practical exercises. And they will have to trade off what can a nation afford, what resources are available, what is politically possible, what is politically acceptable. And those aren't questions which we can really address terribly well. And that's why sometimes, certainly within the energy realm, a lot of researchers get very frustrated because, well, why don't you just do what we say? Because we're right. But the elected politicians have a different perspective, and one that is, well, we can't do something that induces civil unrest. So, and that's why there is always compromise. So coming back to what the sort of things I was showing is that one of the reasons for not having too much detail and not too much granularity was that what you want to do is get the big picture and then say, right, roughly speaking, things are kind of in this order. Now, if you want to do something detailed, if you want to make an actual detailed decision, what we've done is point out what are the important things. Now, let's forget the numbers of my own exercise. Let's now unpack really what's going on there and do a very deep dive into the detail to be able to make a decision. So we've certainly taken the approach that actually what we provide is not the decision that you can't make the decision directly. And we've tried not to do that because philosophically, that's a quite tricky problem because it's not to us to provide, say, just do it like this. So you provide some information and say, right, here's the interesting bit. Now let's unpack it with what you understand about the world, to the politicians or civil service, etc., and how might a actual solution be constructed. And that's been very much our approach, because I don't think, certainly with what we're doing, I don't know how, I was going to say from a philosophical perspective, how you can actually say, this is the route to sustainability, this is the route to security. I think is probably not answerable with that sort of analysis. The numerics only say this is big, this is small, that's in between, that's over there, that's over somewhere else. And from that, you can then use some real people with serious, expertise to say, what does this really mean? How do we implement it? And it's picking the right tool for the job, I think.
Thank you very much, Colin. Mariano?
Yeah, basically, I agree with Colin. There is, in terms of limitations of what we've presented, on the one hand is the data and the uncertainty behind the data. So basically, we are sometimes limited by what is available, not only from the resources availability, but also the transformation. Sometimes we need some additional collaboration with industry, with the government, so that we can actually use better data to validate the models. Apart from that, related to constraints to the models, of course, we all know that the models are really flexible, but we need input from those politicians. We need input just to be able to address certain issues that maybe they are not that technical, but they require to be included so that the solution can be accepted. And that's precisely the need for these kind of committees, so that we can actually present the tools and see if we can improve them based on operation of how we can implement, on how we can use the resources from regional and national governments to that. Another thing is exactly, another problem is the collaboration. From the numbers, basically, we see that larger site collaboration will provide better results, but the problem here is the agents. So everybody wants the best for them, and maybe the best for them is not the best for everyone, but you need to be able to compromise, and you need to be able to accept that and that's also a difficult issue. So you see anytime, I mean, at least you see the news when there is a big negotiation in Brussels between related to any topic. So there are a lot of compromises because of the different ways to see, or the different how you interpret the different constraints. And that's also something that, on the one hand, we can implement their methods, but we need more input to make them real. And that's actually the biggest somehow limitation to what we provide. We can help, but we cannot do it alone. We need the input from the decision makers and the society as such.
Thank you, Mariano. And Aidong, any comments from you?
Yes, just to add to what Mariano and Colin said, I think in terms of the gap between the modeling, the result of modeling studies and the real world actions, I guess there's also a element of working out some fine implementation details. Because I'm taking our work as an example, looking at the potential of indoor farming in different regions. I think we have tried to do as reliable job as possible in setting up the model and making predictions. I think our conclusions should be reasonably reliable in terms of which region might be suitable, feasible, which regions might be struggling. But even for a region which has been identified as suitable for these kind of activities from the energy supply perspective, from the land availability perspective, if any let's say, if any sustainability-minded indoor farming companies wanting to expand the business, I mean, from the modeling results, I think they will still need to work out all details, particularly in terms of, for example, energy supply. You know, how exactly within that particular local environment, how, if you want to have zero low carbon energy to power your greenhouse or plant factory, so how exactly you can get this implemented within that actual setting? Are you going to build your own kind of wind farm or solar farm, or are you going to develop partnership with other businesses, or you're going to just rely on the grid and hoping that the energy mix in the grid will become greener and greener in the next 10 or 20 years? I think these are the details that need to be thought through, need to be worked out before the result of the theoretical learning can be translated into real world action.
Thank you. And I think we can conclude. Let me thank again all the speakers for the interesting presentation and the nice discussion. Thanks again also on behalf of the energy section. Peter, do you want to say a few concluding words?
Just expressing my thanks. Excellent afternoon. I enjoyed it a lot, in spite of not being in the field, but very inspirative, and I enjoyed it. I'm sure that the rest of the audience as well. So thanks, very great thanks to all of you guys.
So thanks again, and see you to the next Spotlight talk. And okay, so goodbye to everyone, and thanks for people attending.
Thank you very much.
Thank you. Thanks for